Right, we're going to start out chapter 7. Don't do 7.1. I don't remember what that section is, but we skip over 7.1. We're going to start with 7.2, but we're going to split it into 2 lessons. So 7.2 starts out with inverse trig. Okay? If you remember when we talked about inverse functions before, we've mentioned that they're a mirror image of each other. So like 2 examples of inverse functions are squaring and square rooting. Those are inverse functions. And if you draw a squaring function, which is a parabola, and a square root function, they would look like this. Here's the squaring function. I only drew half of the parabola because the other half isn't going to make sense when you look at the square root. There's the square root function. So if you look at that black line, or the black curve and the red curve, and you draw in the line y equals x, if you could fold that right on that green line, the right half of that parabola would land exactly on top of that red curve. They're mirror images of each other. And that's true for any 2 functions that are inverses. They're always mirror images over y equals x. Now, when we talk about domain and range, which one is domain? What letter? Yes. Yes. And what about range? Y. If inverse functions basically take y and turn it into x, and they take x and turn it into y, all that happens with an inverse function is the domain and the range switch. So if you know the domain and the range of the original, then the domain and the range of the inverse are switched. That's all that happens. Now, in order for a function to have an inverse, it needs to pass a certain test. It's kind of like the test that we use in Algebra 1 when we ask if something is a function. That's called the vertical line test. The vertical line test says that if you draw something, and you put a vertical line in it, and it only hits it once, then the graph you're looking at is a function. In order for a graph to have an inverse, it needs to pass what we call the horizontal line test. So let's think about the graph of sine. So there's the graph of sine. And the horizontal line test says you can draw a horizontal line and it only hits the graph once. Would that be true here? No. If you draw a horizontal line, it's definitely going to hit the graph more than once. So the problem is if we think about, if we think about inverse sine in terms of the entire sine function, we can't do it. So what we're going to do is, instead of looking at the entire function, we're only going to look at part of it. We're going to try to find a section of the sine graph that does pass the horizontal line test. And we're going to use that section to base everything on inverse sine. Let's try it. Say right there. Does that section pass the horizontal line test?
No.
No. Remember, each tick mark here represents 90 degrees. So this is 0, 90, 180, 270, and 360. That's one full cycle. All right? So that's about 0 to 180. Okay, that doesn't work. Let's try it about right there. Yeah, it's not perfect, but hopefully you get the idea. If you look at that section between those 2 tick marks, then that section passes the horizontal line test, which now means we can talk about inverse sine. Does anyone have an idea what those 2 mark? Well, I kind of said how much each one is. That's my y-axis. And how much left and right of the y-axis am I going? 90. So when we talk about inverse sine, we're going to talk about a section from -90 to 90. So we're going to restrict the domain of the original. I think I write that down right here. To be between negative 90 and 90. That's the solution to make it past the horizontal line test. Now, there's other sections you could use. Negative 90 to 90 is just one of them. You could find other ones. But this is the one that is the standard one we always use. And it's the one that calculators use. Because the whole problem with having a graph that fails the horizontal line test is that if I do inverse sine of 0.5, we expect to get one answer back, and the calculator does give me one answer. Everywhere that this horizontal line hits that graph is a potential answer to an inverse sine problem. So you could get one here, one here, one here, one here. You could get an infinite amount of answers when you do inverse sine if you don't limit where you're looking. That's why we limit where we're looking. So it narrows down how many answers we get to one instead of infinitely many. So here's another example with numbers. Sine of 30. Sine of 150. Here's another one. Sine of 390. They're all 0.5. So you can think of all of these as different answers where the horizontal line hits. But when you do the inverse sine of 0.5, the calculator has to decide which one is it going to give you. Is it going to give you the 30? Is it going to give you 150? Or is it going to give you 390? Well, it's always going to give you the answer that's between negative 90 and 90. That's the way inverse sine works, because that section passes the horizontal line test. Let's go back up and look at that section again. So we're focusing on a domain from negative 90 to 90. How about the range in that section? Yep.
Negative 1 to 1.
Right. So the domain is negative pi over 2 to pi over 2. And the range is negative 1 to 1. That describes what's inside that box. Now that's for the original. When we talk about inverse sine, what did I say is going to happen with the domain and range? They're going to switch. So when we talk about inverse sine, your range is going to be negative pi over 2 to pi over 2, and your domain is going to be negative 1 to 1. Let's graph it and see. But that's exactly what it's going to look like on the calculator. Okay, well, I kind of told you that. But let's graph it first, and then I'll write down what I just said. Remember, inverse sine is sine. Looks like it has a negative 1 up higher. Okay, so we have anything else? Clear that. And let's put in the window. Now, if I hadn't told you that the domain and range are going to switch, you wouldn't have known what to do for a window, but I did tell you they're going to switch. So let's set our domain from, let's do negative 2 to 2, because that was the range of the original, well, negative 1 to 1. And pi divided by 2, that's about 1.57. So I'm going to do negative 2 to 2 again for my range, because I want to go a little bit beyond negative 1.57 and positive 1.57. So it's not right at the edge of the screen. So let's do negative 2 to 2 for that. And I didn't see a good picture here because when we talk about pi over 2, what kind of units are we using?
Radians.
We're using radians. And what kind of unit is my calculator in? It's in degrees. If you wanted to do this in degrees, that's fine, but make negative pi over 2 and pi over 2, make it negative 90 and 90 in the window. Okay? Or maybe you want to go a little bit past it, like negative 95 and 95. Now it should look good. There you go. That's what the graph of inverse sine looks like. It's a mirror image of what's in that box over the line y equals x. Now, most of that graph, if you put in the line y equals x, kind of looks like it's on the line y equals x. And if something's on the line of reflection, it doesn't really move. That's why a lot of it kind of looks the same. But it is a little bit different at the ends, because towards the end of the curve, it isn't quite on the line as much. But that's what the graph of inverse sine looks like. So the domain is negative 1 to 1, and the range is negative 90 to 90. Sometimes I have a hard time remembering it, so I always think back to the original. And I say, okay, original sine has a range of negative 1 to 1. So that means inverse sine has a domain of negative 1 to 1. They just switch. Let's think about inverse cosine. Let's draw a regular cosine and just kind of see what that looks like. So that starts, it looks something like that.
Sorry, what was the range again? What you said was the negative 2 by the 2 by?
The range of inverse
Pi over 2, that's what I meant.
is the domain of the original, and we restricted it to the negative pi over 2 pi over 2. And notice I put brackets on that because it does include negative pi over 2 and pi over 2.
Mm-hmm.
All right, so there's your graph of cosine. Let's pretend like we put a box around negative 90 to 90, and let's see if that section passes the horizontal line test. There's negative 90 to 90. Does that section pass the horizontal line test? No. Then when we deal with inverse cosine, we can't base answers off negative 90 to 90, because we could get more than one. Let's try about right there. Does that section pass the horizontal line test?
Yes.
Yeah, and so do infinitely many other sections. So with that one. But that's the one they use. That's 0. Anyone have an idea where the right edge of that box is? 180. It's halfway through the cycle of cosine. Here's where the cycle ends. Here's where it starts. You are halfway. So when we deal with inverse cosine, that's going to be our restriction. So for the original, the domain is 0 to pi. Now this is the original, not the inverse. That's the restriction we need to use to pass the horizontal line test. And what's my range there? Negative 1 to 1. That's the original. Okay, now let's talk about inverse. When we deal with inverse cosine, what is my domain going to be?
Negative 1. That's supposed to say negative 1, negative 1.
Yeah, negative 1, sorry. So,
Negative 1.
yes, when we deal with inverse cosine, the domain is going to be negative 1 to 1. And what's the range going to be?
0 to pi.
0 to pi. Again, the big picture, the whole reason why we're doing this is because if we don't limit it there are infinite amounts of answers. That's where these restrictions are coming from. We're forcing the graph to pass the horizontal line test. All right, now let's think about tangent. So tangent is one, remember, that looks totally different. Does the graph of tangent pass the horizontal line test? No. Then, in order to do inverse tangent, we need to find a section that does, and we're going to base all our answers on that. Okay, so let's take that. Let's make a box about like that. And let's try, okay, so there's more tick marks here than we're used to seeing, but that's okay. Let's move the box. I can set the tick marks so they're used to what you would normally see. Let's do a tick mark every pi over 2. I think that'll make it a little easier to look at. Okay, so now each tick mark is 90 degrees apart. I'll do my box again. Okay, so I need a box. Something like that. Let's try 0 to 180. Here's 0 to 180. If you look at just that section, does that pass the horizontal line test?
Yeah, I think so.
Yeah, I know it's kind of weird to look at, but if you block everything else out, you kind of see it better. There's 0 to 180. Yeah, that section passes it, but it breaks it into 2 pieces. So what we'd rather do is focus on a section that doesn't break it into 2 pieces. And we're going to do that. Actually, I think this works even better. We're going to do that by focusing on that section. Does that pass the horizontal line test?
Yes.
Yep. And is it all one piece?
Yes.
Yeah, one piece is better. So what do you think we're going from what to what here? Okay, so the domain here is negative 90 to 90, including or not including the endpoints of that?
Including.
Well, what's happening at negative 90 and positive 90? We have vertical asymptotes, so you can't include those. So this time the domain, this is original tangent, this is not the inverse. Domain is negative 90 to 90. What's the range? All real numbers. So in original tangent, we have vertical asymptotes. What do you think is going to happen with inverse tangent? Horizontal asymptotes. Everything switches. So we're going to have horizontal asymptotes. And the graph is going to look more like this. What's going to be the domain of inverse tangent? Right, inverse tangent is going to go left and right forever. So the domain is going to be all real numbers. And the range is going to be negative 90 to 90. Negative pi over 2 to pi over 2. Those two numbers, negative pi over 2 and pi over 2, those are your asymptotes. If you want to see it better, you can do a better picture of it. Let's graph inverse tangent. So your domain goes left and right forever, but it's going to have horizontal asymptotes at negative 90 and 90, or negative pi over 2 and positive pi over 2. Any questions about what the domain and range are? Oops, too small. For inverse sine, inverse cosine, or inverse tangent? everything we do is based on those domains. So like if I said to you, I want to take inverse cosine and shift it up 1. Okay, well now the new domain would be, or the new range, if you shift inverse cosine up 1, would be from 1 to pi plus 1. But if we don't know those originals, we're not going to be able to shift them. Okay, when you do something like this, when you take a value, perform an operation on it, and then perform the inverse of that operation on it, what do you end up with? You end up with the original. Exactly. So if you take the inverse sine of the sine of some value, you will get back the original value. But remember, there's restrictions. We put these domains in place. Let's try a value. Let's try the inverse sine of the sine of, and I'll do it in degrees just so we can see nice numbers without decimals. Let's do the inverse sine of the sine of 30. You get back 30. So the inverse sine and the sine canceled out. What was our restriction? If you think about original sine, that we had to stay between, so we passed the horizontal line test. Negative 90 and 90. So if you do the inverse sine of the sine of any number between negative 90 and 90, it will work just fine. You will get back exactly what you started with. If you go beyond that, somebody give me a number that's not between negative 90 and 90. How much?
91.
91. Okay. Didn't get back what I started with. There's a pattern to what you get back, but it's not what you started with. What's that? Yeah, if you put in 120, it wouldn't work. So when you take the inverse sine of the sine, you will get back what you started with, as long as you started with an angle between negative 90 and 90. Now, let's try it the other way. This is just an order of operations thing. Now we're going to do the sine of the inverse sine. If you take the sine of the inverse sine, let's do like 0.8. I got back 0.8. I got back exactly what I started with. But there's a limit to when that works. Think about our inside function. So think about inverse sine. And what did we say the domain was for inverse sine? Yeah, if you can't think of the domain of inverse, think of the range of the original. So the range of original sine is negative 1 to 1. That's when that formula works. Try a number that's outside that. Somebody give me something that's not between negative 1 and 1.
Negative 2.
Negative 2. Now, when we did that before, we just got back a different number than we started with when it was outside the bounds we needed to use. Here, you can't even do that. Because imagine, think of sine. What's the highest and the lowest that sine goes?
1
and what?
Negative 1.
Negative 1. So imagine putting a horizontal line at negative 2. It's like asking this question. Here's your graph of sine. There's a horizontal line at negative 2. Where do they cross? Never. So when we're talking about the type of function where the inverse is on the inside, if you don't stay within those bounds, it won't even work. Not that you'll get a different answer back, just won't work. Okay, so same idea here. Inverse cosine and regular cosine do cancel each other out. And we'll get back what you started with under certain conditions. The condition is always the domain that we set for the inside function. So what did we restrict the domain of cosine to? So that its inverse was a function.
0 to 180.
0 to 180 or
0 to pi.
And that's the one, if you pick a value that's not between 0 and pi, you will get an answer back. It just won't be the one you started with. Cosine of inverse cosine, those cancel each other out. But what does x have to be between? Think of the domain of inverse cosine. Right. Domain of the inverse is the same as the range of the original, which is -1 to 1. Now, up till now with sine and cosine, we were able to use equal to's. We can equal the endpoints. When we get to tangent, what happens in the graph of tangent that doesn't happen in the other functions? Asymptotes. So now we got to be careful about whether we include or don't include something. Yeah.
Why is the domain on 1A restricted to -pi/2 pi/2?
We talked about passing the horizontal line test, finding a section that works.
Is that the only section that works?
Is it the only section?
There's more
No,
sections.
there's infinite. There's infinite.
Yep, infinitely many.
It's just the original one.
What's an example of another section that would work for 1A?
You asking me?
I'm asking them.
Ah,
Pi over 2 and 3 pi over 2. Or no.
I think that would be correct.
Yeah.
so you could shift it every 360 degrees. You could just shift it to the next cycle, but there's another one within the same cycle too.
I think you're right. Pi over 2 and 3 pi over 2.
All right. Inverse tangent, regular tangent, cancel each other out. What's the domain that we restricted tangent to? So the inverse had a function. What's the inverse was a function? The original. What's the domain that we restricted the original tangent to? Including or not including? Not including. Big difference. So -pi/2 to pi over 2. And tangent and inverse tangent will cancel each other out. As long as, what's the domain of inverse tangent? All real numbers. So this formula, I'm just calling it formula 3b. That formula works all the time. There's no restriction on it. And you might kind of be thinking, well, when do you use something like, when does this kind of stuff come up? Well, let's do it like this. The only way to solve that equation for x is to get rid of the tangent function. So the way you get rid of the tangent function to isolate the variable is with inverse tangent. So inverse tangent, let's pretend that was in degrees, because in degrees you can be -90 to 90 and 5 would be fine. And that's when you would use something like formula 3a, when you're trying to solve for a variable in a trig function. Okay, any questions on that? Actually, that would just be a 5. We're not really getting into that too much today, but that's an example of when you use it. Right, so transformations of inverse trig functions work exactly the same as every function we've done all year. So I'm not going to write everything down, but I will go through it. That could be an inverse sine, inverse cosine, or inverse tangent. It could be any one. What does A do? That's your horizontal shift. And plus would move it to the left and minus to the right. What about B? Stretch or compression. If you make B really big, what would happen to the graph? What happens? The bigger you make b, the more it compresses. The bigger and bigger b gets, the more and more it compresses. If b is a negative, what does that do? Flips it over which way? Like horizontal or vertical? Yeah. If b is negative, that's a horizontal reflection. What about c? Vertical stretch, and that one is the bigger you make it, the bigger it stretches. What if c was negative? That would flip it vertically, because it's a vertical stretch. So flip it vertically, which is over the x. And what about d? Shift, yep, and positive would move it up. Negative, down. So it's exactly the same as everything all year.
Right, okay, so and B was horizontal stretch.
Yep. So the way we're going to figure out the domain, say we had something like this, or like this. We're going to find the new domain and range. Of course, if you're only doing one transformation, one of these is going to stay the same. The way you find the new domain is you're basically going to create a compound inequality. Let's say you had to do this. Inverse cosine of 2x. The argument there is 2x. That's going to go in the middle. On the left and on the right is going to be the original domain, So for cosine, let me think. The domain is the same as the range of the original. That's -1 to 1. So you put the original on the outside, put the argument in the middle, and now you solve it. So the new domain of inverse cosine 2x is -1/2 to 1/2. -1/2 to +1/2. But that's how you find the new domain. Put the argument in the middle, original domain on left and right, and then solve for x. Now, the range, you could do it more mathematically. I don't ever really think of it that way. I just think of it as, did I do any stretching? And then did I do any shifting? In that order. So here's an example. Simple numbers. Let's say I had a range that was -2 to 2. And I stretched that by a factor of 3. Each of these numbers would get multiplied by 3 if you made it 3 times the stretch. So if you stretch that by a factor of 3, what would that turn into? Yeah, it would turn into -6 to 6. And then let's say you shifted that up 1. Well, each of these numbers would go up 1. So -6 would become -5, and 6 would become 7. So that's how I figure out the range. Figure out if I did any stretching first, and then any shifting last. Do you have to follow the order? C first, then D. Alphabetical order.
Wait, sorry, how would you solve that domain with the 2x again?
We're gonna do one right now with a 2x. Yeah. All right. So the first thing I look at is that, and I try to figure out, is that changing the domain or is it changing the range? One of them is going to stay the same because I'm only doing one transformation. This is a horizontal stretch or compression. Stretching or compressing horizontally is going to change the what? It's going to change the domain. So the range in this problem stays the same. What is the range of inverse sine? Yep. Yep, it's the domain of the original. -π/2 to π/2. Now let's solve for the domain. Put the argument in the middle. And put the original domain on the left and right. What's the domain of the inverse sign?
Negative pi. Negative pi over 2 pi over 2. Isn't it? Negative 1. Oh.
Domain is negative 1 to 1 for inverse sign.
It was the.
And how would you get x by itself there? Divide everything by 2. So as an inequality, the domain is negative 1/2 is less than or equal to x, which is less than or equal to 1/2. How would you write that as an interval? Yep.
Close parentheses, negative 1/2 to 1/2, close parentheses, or bracket.
Bracket. When you put a 2, that causes the graph to compress by a factor of 2. So instead of being negative 1 to 1, it should be half that much because you compressed it. And that's it. That's your domain and range. Let's try this one. Okay, what kind of transformation do we have here?
It's the same one as this
Yep, which is, what's it going to affect? Yep.
Horizontal stretch.
Yep, that's going to be a horizontal stretch. It should stretch 3 times as big. So if you know the original domain, you should already kind of know the answer. But we'll go through it. Start with the range. And remember, it's inverse sine. What is the range of inverse sine?
0. Negative pi over 2.
Yeah, when you do the 0 to pi, that's the cosine. So it is negative pi over 2 to pi over 2. And the domain, put the argument in the middle. And we just did it in the last problem. What's the original domain for inverse sine? It's negative 1 to 1. And how are you going to get x by itself there? Yeah, multiply everything by 3. Times 3, 3, 3. So your new domain is from negative 3 to 3. Because you've stretched it by a factor of 3. 1/3 is a smaller number, makes the domain bigger, stretches. Okay, question on that? Let's try something. Let's do an inverse cosine. Okay, what's that plus 2 going to do?
Attention please, this is just a reminder that juniors should be happy.
So what's that plus 2 going to do? Vertical shift, which is going to affect the range. So domain stays the same. What is the domain? That's this diagram right up here with the A, B, C, D.
Oh, okay.
Because it's a plus 2 at the end. So since it's a vertical shift, that's going to affect Y, which is your range.
I see. Okay.
What's the domain for inverse cosine?
Negative 1, 1.
Yep. Domain of the inverse is the range of the original, which is negative 1 to 1. Okay. What's the range of inverse cosine? Okay. Originally it's 0 to pi. And what are we doing with that range? Yeah, we're just adding 2. We're shifting that range up 2.
Yeah. Okay.
So what's the new lower end of the range? 2. And the higher end? Pi plus 2. Shifted it up 2. Question on that one? Alright, try this one. Then I think I have an inverse tangent we can do. So let's see. Here we've got a 5 in front. What kind of transformation is that? Vertical stretch. And vertical stretch is going to affect the
That's the range.
range. It's
And
going to affect the range. So we can copy the domain down if that stays the same. What is the domain of inverse cosine?
-1.
-1 to 1. What's the range of inverse cosine? 0 to pi. And we're stretching it by a factor of 5. So the lower end is going to be at, and the upper end? 5. And this one. Well, the domain of inverse tangent, you should be able to get that one right away. What's the domain of inverse tangent? It's always all real numbers. Doesn't matter how you stretch or shift it. It starts with all real numbers, it ends with all real numbers. So which number here is technically a transformation on the domain, but it doesn't matter because it's inverse tangent? The 2. So we don't need the 2. This 2 has no effect on the answer to this problem. The 3, though, is a vertical stretch. What is the range for inverse tangent? Negative pi over 2 to pi over 2. But how is it different from? It does not include them. So we're going to have parentheses on the range. And what are we doing with the range? What's the transformation? Multiplying it by 3. Stretching the range to be 3 times as high and low. So what's my new range? Yep. 2. 3 pi over 2. So that's your domain. So as long as you know the original domain and range, it's not that hard to figure out a transformation of it. If you don't know the original, then yeah, it's hard to figure out. Any questions on that? Okay, so we're the last 2 things. Yeah. So here, I just want you to identify the transformations. But there's something you might want to do first. Because this problem is not written quite in that format.
Yeah.
Yeah. So this argument inside here would really become what? It's 2 there. So those are the numbers you want to focus on when you're talking about the inside numbers. The 3 and the -5 are fine. So how many transformations are happening?
4.
Yep, all 4, without any reflections, I don't think. So first transformation, we're going to shift left 2. Let's go and see if you can see it. Okay, so shift left 2. What's the next thing? Stretch by how much?
Compress it by stretch it by 4.
You could say, yeah, I would say that's really a horizontal stretch by 4. So horizontal, it's backwards, just like the +2 brings it left instead of right. It's horizontal stretch by factor of 4. The other way you could say that is you could say compress by 1/4. Now that's like saying move down -2, so now you're using a double negative, it just gets confusing. So instead of saying compress by a fraction, just say stretch by an integer. Okay, what's the third thing? Yep, vertical stretch. Need a little bit more there, yeah, by factor of 3. And the last thing?
Just down 5.
And if you say down, down automatically means vertical. So you could just say shift down 5. Same thing here. You can just say shift left 2. You don't have to say shift horizontally left 2. Okay. Any questions on identifying transformations?
What was the fourth? Oh, sorry.
Shift down 5.
Yeah.
And the last thing is just how to plug in an inverse trig function on the calculator and get an answer.
Right.
So let's try, I have 3 of them. Yeah. Let's try the inverse sine of 0.5. So to do this, you just use your calculator. How do we get an inverse trig function? What do you have to press? Second, and then the trig function. Now, my recommendation would be to always do it in degrees first. If they want radians, convert it manually. Because if you do it in radians, we've talked about this before, you're going to get a decimal. And you're not going to recognize, most likely, that 0.5235987756 is really pi divided by 6. The only reason I know it's pi divided by 6 is because I did it in degrees first. I saw the answer was 30, and then in my head I just multiplied by pi and divided by 180 to get pi over 6. So when you're doing inverse trig, you are solving for an angle. So if you do a degree, put the degree. You need to put the symbol. If you're doing it in radians, do not put 0.52359877.
Yeah.
Put pi over 6.
Either one is an acceptable
Yeah.
answer though, right?
And I could do this one because it comes out nice. If it doesn't come out nice when you do it in degrees, well then it's not going to come out nice when you do it in radians. In that case, a decimal is fine. But check the degree first, because if it's going to come out nice somewhere, it's going to be in degrees. So inverse sine of negative 0.7. Okay, that's not a nice number in radians, but I told you to do it in degrees first. So let's check it in degrees. Well, it's not a nice number in degrees either. So in this type of problem, rounding to 2 decimal places is fine. There is no way to write an exact answer. So it's about negative 44.43 degrees, which is equivalent to about negative 0.78 in radians.
Sorry, how did you find that? Just do it in radians instead.
Yeah, I typed the same thing in, I switched the mode on the calculator. So I wouldn't ask you to find an exact answer in a problem like B. Okay, inverse sine of 1.2. What's the domain of inverse sine?
Because it only goes negative 1 to 1.
Domain of inverse sine is only negative 1 to 1. We tried something like this earlier when Mr. Babb was in here, and I showed you can't do that. You get an error. This is outside the domain. So this, there's no solution. And inverse cosine and inverse tangent would be the same. Second cosine, or second and then tangent. Okay, and that's 7.2 purple. Any questions on that? That's it. Okay, so the homework tonight, those questions 1 through 9, 13 to 20, 22 to 24, and 27 to 33.
Also, when you're trying to